That's 10 right now. Another thing is I just posted the grade for homework 1. And I noticed there was one student who has problems to access the internet, and still, I mean, the submission hasn't been made yet. So basically, I would like to ask you to submit it as soon as possible, because um, for such kind of case, it's reasonable to give you a chance to resubmit it. But I need to post the solution soon. So please submit your homework as soon as possible, such that I could post the solution soon. All right. Any questions regards the homework or the learning? I mean, the classes so far. Okay, sounds good. And another question for you is the um, Autodesk Fusion 360. I would like to start a poll for you guys. See how much of you need some tutorial or support to get to know the Fusion 360, or you've already had experience with it. Let me start a poll. Just 1 second. So such that I could arrange, I could talk with the Autodesk people for some free study material of 360. Basically, I will ask you, do you need the some study material? Basically, these are the online videos, right? Online video tutorials. For Fusion 360, because the reason for me to ask is it may require some resources, so they want to know how much you want to how much you want to need that, how much you want to take from that from them, such that they could prepare. Just 1 second, I'm typing the poll question. Single choice, multi-choice. Yes. No. I think that's it. All right, I've launched a poll about the Fusion 360. Please, wow, I see what almost 100. Okay, 90 something. Okay, good. So if that's the case, I will definitely ask for basically the whole class to have the access to the study of the Fusion 360. I will definitely arrange it and let you guys know. So that's another thing I want to mention before the class. Anything else? Any other questions? All right. Okay, let's move on and start the lecture. Just 1 second. Let me. All right. Let's say. So in today's lecture, let's talk about some computational elements of 3D printing. And this kind of computational aspects are usually universal. That means it go across different processes. and they are very important. They are another fundamental another foundation for 3D printing. One is the process material and the mechanical parts, right? The other one is this computational elements. So let's look at it. So basically, we would like to talk about some of the file format for 3D printing, and also the transformations for CAD model, because for when you do the CAD, there could be one specific orientation or position, or even size, right? But when you transmit the file into a 3D printer, you want to consider about the orientation, because it is essential to generate the tool paths as well as the support material. So sometimes one orientation of the object would require a substantial amount of support, but for another orientation, it does not require any support at all. So that is essential for you to play with those transformations, right? So that's why we want to learn about the some of the trigonometries and also the matrix operations to manipulate the CAD model. And then some other aspects such as the slicing. So you all know in the 3D printer, 3D printing, the material is accumulated layer by layer. Then for each of the layer, what would be the tool path, or what would be the slide look like, how it is generated. So that's another important aspects in the computational elements of 3D printing. So let's look at them one by one. The first thing first is the representation and file for 3D printing, right? I mean, because you guys have already played with Prusa 3D printer, right? So you know, for Prusa, it requires the STL file, and then the software will generate the G code, and the G code eventually will be transmitted to the 3D printer for actually 3D printing. But the file format to represent the 3D shape is usually the STL file, right? So in the STL file, a 3D object, it actually is represented by polygon patches. And usually the polygons are triangles. This is the most widely used polygons in those files. As you can see here for this wrench, I don't know, for this mechanical part, sorry, in the system, what actually it is like this. It's a series of triangles and composed together. And that's how this 3D shape is represented. And obviously, if you have a smaller polygon, the shape, the accuracy or the shape approximation of the file versus its original design will be smaller and smaller, will be better and better. So basically, there is one process which is called tessellation. So when you do the CAD in the CAD software, I mean, no matter SolidWorks or Fusion 360, basically you are dealing with the so-called parametric surfaces. So for the parametric surfaces, you can understand it. It's like you have an equation. You have a mathematical equation to represent that surface. That means there's no error at all. That is an exact representation of the shape, right? But from the parametric representation to this polygonal representation, or more specific, triangular representation in the STL file, you actually need to use those triangles to approximate the original parametric surface. So from a equation, mathematical equation, which is 100% accurate to some approximation, there will be some approximation error, and there will be losing some accuracy. So that's why this tessellation will introduce some problems, especially in the accuracy and shape approximation error. And I will introduce that in the later slides. But just at this moment, just keep in mind the polygonal file you use is not the most accurate representation, but it is suitable for the computation, the following computation. It would be difficult to still use the parametric representation, which is used in the CAD software to do the job for the 3D printing. So that's why we need this tessellation. And I will introduce those operations one by one, and you will understand why we still need this polygonal representation of the surface. Any questions so far? Okay, let's move on. So if we open a ASCII STL file, so you will see something like this. This is the file format, and because the STL file is so, I would say, well, it's not well established, but it has been used for a long time. So it became a industry standard for transferring the CAD model to some rapid prototyping system or 3D printing systems. You could there could be both ASCII or binary format for the STL file. So basically, the binary format is just the binary numbers. It is encoded to the binary numbers from the text. So it's not readable. You won't understand what it is. So usually, if you want to understand what is in this STL file, you probably want to have a ASCII STL file. So how it look like? So first of all, it has some keywords. It has a hierarchy. So basically, this whole model in STL file is represented by the keyword solid. And this example is the file name. So that means, well, there is a file example or model name. There's a model named example, which is a solid. And this is the highest hierarchy, right? And then the rest will be simple. So basically, as you see in this figure, basically the whole model is represented with a series of triangles, right? In this case. So basically, what's the next in the file are each of the triangles. So again, starts with some keywords, facet, and facet, actually the keyword is facet normal. This appears as a whole, right? So this is the normal of that triangles. So what is normal? Basically, if you have a triangle in the space, and basically a triangle will stay on a plane. So for a plane, there will be a normal vector, right? So basically here records the normal vector of that triangle's plane, right? Yeah, and another thing is this for the STL file, usually this normal will be the one point outward. So like a shape, maybe go back to here. So because normal has two opposite direction, you could go this way, or it's total opposite direction this way, right? And if this side is the outside of of the object and this side is the inside of the object, basically this normal vector will be this one. So that is so-called the outward normal vector. So that is what this normal vector record. All right, and any question about this? Okay, good. And then this is another keyword, outer loop. And in this outer loop, the three vertices which compose the triangle will be recorded, because for each triangle, right, there will be, oh, that's so bad at drawing. Let me redraw it. Just 1 second. Let me use the touchpad. That will make drawing better. So let's see there's a triangle. So for the triangle, what you have will be the three vertices, right? And basically here, the keywords vertices record the 3D coordinates in the X, Y. Of course, there will be a coordinate systems, X, Y, Z. I don't know where, how to set it up, but I mean, it could be set up like this, X, Y, Z. And with respect to this coordinate system, each of the vertices will have a 3D coordinates. And here represents the 3D coordinates. And after the three vertices are recorded, there's another keyword, end loop. And that means, well, this three vertices are recorded here, and end facet. That means this triangular facet, all the information you have recorded, including the normal and the three vertices coordinate system. So this will be repeated again and again until all the triangle facets are recorded. And the last line would be, just 1 second, what happened? The last line would be end solid. It doesn't appear here, but there will be a last line which is end solid. That means you have basically you have complete the representation of the whole model. So that's it. That's how this STL file represents the 3D shape. Another point here is when you record the three vertices, how you order them. So actually, how the way they put the three vertices here actually implies an order, which is the counterclockwise order. So that means if this is the vertex 1, vertex 2, and the vertex 3, basically, if we order them 1, 2, 3, I mean, with respect to here, and here, it suggests, let me draw the triangle here. That's really bad, but you get the point. That is, and the normal vector is like this. That is, if you use the right-hand rule, starting from 1 and turn to 2, turn to 3, your thumb position, I mean, you all know how to use the right-hand rule, right? So the thumb position, the thumb direction will be exactly the normal vector's position. So actually, this is this gives you the normal. If even you don't have this facet normal, you could reconstruct it by only using the three vertices and its order. So that's a hidden information. That is what usually most of the STL file will follow. Any questions about this? Okay, good. So basically, most of the CAD software would support the export of STL file, and I just show how it works in the Fusion 360. Basically, you choose file, 3D print, and under the selection, there will be some options, some menus for you to export the 3D object to STL file. And some parameters you want to tweak. For example, the refinement, that represents how much triangles you want to use for representing this shape. And as I mentioned, if you put higher, that means there will be more triangles. And it turns out the shape approximation error will be smaller. So if the file size is not too big, you want to always select a high refinement. But that could be exceptions. I mean, for example, you have you export a really large file with too many triangles. That will cause problem for the slicing and the toolpath generation. That's not desirable. But that happens really depends on the model, the geometry of the model. Usually you can select high. All right. And then Ncheck send to, that means it will output to your local desktop, I mean, local computer. And then click OK. That will give you the file exported. Of course, there are other options regarding the normal and also some of the approximation error and aspect ratio. I recommend you do not touch these unless you are 100% sure what you are doing. Basically, this is related to the shape approximation as well. And if you do not understand how you change these will affect your final file, then leave it as default and just change this refinement. When you choose different options, these will be adjusted accordingly by the software itself. All right. So similarly, in the SolidWorks, there is options to export the STL of and remember you could have the option to choose either binary or ASCII code. Also the units, that's essential, right? I think you guys, if you ever take my the material processing class, when I teach the class in the lab about the SolidWorks, there's always case, well, the units are different, right? Sometimes you set students set it to be inch, or some students set it to be millimeter, and that will scale the model in differently, right? Turns out if you just do the modeling, it won't. I mean, it makes not much difference. But if you talk about the actually manufacturing, that means you will have a different size for the model to fabricate it. And sometimes it is too big or too small, right? If you mistakenly put the unit there. So be aware of it. Also, for assemblies, that is another tricky part. Basically, if you want to print the object in a whole, then you can save all the components of assemblies. Otherwise, if you want to print each of the assembled parts one by one, then you want to export it component by component. and that will export different files for each of the assemblies. All right, and I mean, you can always play with these options and see what's going on. So for the STL file, as I mentioned, there are some details, right? So first of all, if you look at the triangular triangular mesh file, actually you realize there will be some adjacent facet. For example, this one and this one, they actually share same edge and also share same vertices. But in STL file, there's no such adjacent the adjacent information stored. So it will take the two triangles a separate one. That means when the file to write the information of this triangle, it will record the 3 vertices and a normal vector. And when it goes to this file, this triangle, it will record the 3 vertices again and also the normal for this triangle again. So it does not know this one and this one actually are the coincident vertices. I mean, actually in this case, these 4 vertices are coincident, right? If we talk about this and this. But in STL file, it won't know this. Because basically the file just want to be very general and simple to organize. Actually, if you import the STL file in some of these 3D printing software, it will merge these vertices automatically for you. So that is what you want to keep in mind. Actually, each of the triangles in the file of STL are independent to each other. All right. Another thing is what I mentioned previously. So the vertices for each of the facets are listed in a counterclockwise direction. And according to the right-hand rule, you can easily figure out what is normal direction by finding out what's your sum pointing direction. And also this sum pointing direction is outside of the part volumes, right? Which is identical to this surface normal vector. This is another thing you want to keep in mind. All right. So basically, I think I have talked about this, right? And another thing will be these two basic rules actually helps you in the some of the computation, such as the slicing. So if you have 2 triangles, right? Let's see this one. Which one we talk about? Yeah, this one, T1, right? And we have 3 vertices are listed, V1, V2, and V3, right? And another triangle 2, we have another 3 vertices listed, V1, V2, and V4. So using what I mentioned, the right-hand rule, so the normal direction for the T2 will be, if you use this right-hand rule, you will realize, well, basically you will have the normal direction pointing outward from the paper, from the screen, right? If we talk about the T2, right? Try to use your right hand to figure out what is the normal direction for this facet. V1, V2, V3, right? That's the vector pointing outward to the from the screen. But if we look at V1, V2, and V3, still use right-hand rule. So you will immediately realize, well, this one seems suggesting a normal direction pointing into this screen. And for the two adjacent triangles, basically T1 and T2 are adjacent to each other. That's not correct if you have if you have two triangles have two opposite normal vector, and that means you probably have one of the triangle flipped normal. So that is very useful to for the slicing. And why that's critical? Because for the slicing, to generate the contour of the slice, it will need the normal vector to decide what is the what is the interior of the contour and what is the exterior of the contour. So basically you want to put material inside of the contour instead of outside of a contour. So the normal direction will help you to do this. So in that case, if there is a flipped normal, it will generate a really, I mean, actually a error slice, and such that it will make the printing failed. I mean, actually, I would say the newest softwares or the current software could somehow handle such kind of error cases. I mean, the flipped normal. It will automatically check it and fix this kind of problem automatically in most of the cases. But in the like I would say like 10 years ago when I first used 3D printer, I mean, it's pretty old 3D printer, and also the software, the algorithm there are not up to date. They didn't consider about such kind of flipped normal cases. And so what it generated is, for example, if I have a contour like this, if this is a contour, so then the printer will first scan this contour and then fill material inside this, right? Drawing is really bad. Let me remove it and redraw it. Basically, you will have this kind of filling patterns, right? That's the correct thing, right? But what I end up have is something like, so you get my point. There are some portion go outside of the model, go outside of the contour, like these regions. That is because probably here there are some flipped normal. I mean, there are some triangles with flipped normal, and that failed the algorithm to check inside outside, and turns out the printer think, oh, okay, this is inside, and there's some material printed here. So that's the case why this critical, this normal direction is critical, and you want to keep it correct such that there will be no problems in the printing. All right. Any question regarding this?
Yeah, Professor. So
Yeah.
one question.
Yeah.
So the proper way to, if you were like listing the vertices, would be like V1, V3, V2. Would that correct?
Yeah. Yeah. Correct. Exactly. Basically, you just try use the order and use the right-hand rule to see what is the normal direction, and whether this normal direction makes sense or not, right? That's how you look at it. So this is what I mentioned, the ASCII STL file. Let's skip this, and you want to check this if you want to look at the detail of this STL file. And here shows you an example of a cube. So a cube has in total, if in this case, I think there are 12 triangles. Yeah, there are 12 triangles, but there I only list the 3 triangles here, so it's not complete. But you should be able to understand there are 12 triangles to represent a cube, because for each of the facet you want to split it to 2, right? That's 1 triangle. And same thing happens to all other facets. Also, the 3 facets you are blocked, right? So these 4-sided polygons will be separated to 2 triangles. So in total, 12 triangles, and they will be listed one by one, just as what are showing here. All right. So these are the STL file. So I don't want to go to too much detail about the binary STL file, but one thing is, so for each of the information in the ASCII STL file, it could be encoded using certain binary number, and they could be written into the binary file, and even you have a binary code, and as long as you know the corresponding between the text and the binary number, you could decode it easily, and that shouldn't be an issue to process a binary STL file if the format is determined. All right. So another thing is the shortcomings of STL file. So as I mentioned, if you use STL file, it's kind of an approximation of the original true surface you designed. So if we look at this 2D case, basically we use the curves to represent the 3D surface, and use those line segment to represent the planes or the triangles. So you will immediately know there is an error occurs, right? So between this straight line as well as and this curve, there's a distance. So that actually represents what is the shape approximation error look like in a 2D case, right? So in 2D, that is the distance between the curve to the this line segment, straight line, right? So if we talk about the 3D surface, that will be the distance between the surface, 3D surface, to a plane, and that's the shape approximation error. And in STL file, this cannot be avoided because you are always using those planes to approximate the actual 3D surface. So you can only reduce the shape approximation error by increasing the number of the facets, the triangles, to such that you will have smaller and smaller distance. But you can never avoid such kind of error. That is one thing you want to keep in mind, and that's why I recommend you to set a high refinement when you export your file from the CAD software, right? So basically here gives you the kind of how this error could be computed. That is, you want to take this as a chord, of an arc, and basically you want to find out the this distance, and this line segment is perpendicular to this chord, and this will be your error. So basically, you just want to, I mean, for here, I don't require you to compute the error, but just to understand the concept, because in the real case, it's more complex than what I showed here. But the concept is similar. Basically, just use this distance to measure the error, shape approximation error. So another shortcoming for STL file is its redundancy. As I mentioned, each of the triangles are recorded separately, independently. But actually, in this case, there are a lot of duplicated information. For example, for these vertices, it is recorded for a fourth time, but actually it's the same vertices. And similarly to these ones are duplicated by 2 times, right? Because when you write this triangle, this triangle, this triangle, this triangle, these vertices will be recorded once again. So that sometimes will cause problem because of the triangle size could be quite big, quite large, and that means you have a lot of redundant information. So if we compare the file size of a same model using different file format, you can immediately see the STL file takes the most memory space. So for the binary one, it's better, takes 3 megabytes file space. And for the ASCII STL, it takes even more, up to 11 megabytes file size. But for other software, for other file format, it takes smaller file size memories, because they reuse some of these informations instead of just keep those redundancies. Another redundancy here is the surface normal information. As I mentioned, in the order of the 3 vertices actually suggest the the normal direction vector, and also use the 3 vertices and its order. You could form 2 2 vectors and use the cross product. You can produce a normal vector, and that means there's no need to record this normal the normal vector information. But still, in the STL file, there is the normal information stored. So that's also another redundant information here. All right. So the third problem for STL file is the roundoff errors, right? As I mentioned, there will be a shape approximation error when you tessellate the 3D model to a STL file. And that will introduce the roundoff numbers, roundoff errors if you do a tessellation. And usually it doesn't matter, but for some parts which require really high precision, that could make the printing, make the part unsatisfactory for some certain applications. Then you need to always think about whether this tessellation is good enough in terms of the shape approximation, and also considering the roundoff errors. That will be an issue as well. So another place for the roundoff error could make difference is, as I mentioned, where's my pen here? Okay. So let's see, you have triangles, adjacent triangles. So if these 4 triangles are adjacent to each other, and actually this and this vertices are coincident to each other, right? When the STL file is imported by some other software for slicing or toolpath generation, the first thing they will do is to merge these duplicate vertices. And that requires a numerical computation to compute the distance between the 2 vertices and see whether the distance is smaller than the very small threshold. Otherwise, consider the 2 vertices are 2 different vertices. So that will rely on this precision or accuracy of your shape approximation. And if there are some roundoff error or shape approximation error, which are big enough to make the distance too big and bigger than the preset threshold, that will make problems for the gaps and disconnectivities. That's actually very serious problems for many algorithms, especially in the some softwares which does not consider about it. So in that case, the roundoff error is another very important shortcomings for STL file. So that's why people are looking at some alternatives. As I mentioned, the STL file has a really long history, and it is as what it was defined many years ago. But with the new development of the 3D printing processes, as well as the computational methods around 3D printing, I mean, it's kind of out to date, right? So people are looking at some new options, some new file format. Basically, that there are ways to directly work with the CAD file, which is the exact 3D shape, to do some slicing or other operations. That will avoid the shape approximation and the round of errors in many cases, right? Also, those CAD modeling softwares have its own file format, and they built around their file format for 3D printings. I mean, similarly, they have some exchange file format from those CAD modeling companies. And I mean, depending on how popular the software is, those file format get different popularity among the industry and academia. Also, those standardization organizations, they define some neutral interchangeable format like IGS step file or ASTM F42. These are some open source neutral interchange formats for the 3D shapers. But I mean, it really depends on how popular these files are used. Sometimes those file format defined by the CAD software companies or 3D printer companies got more popular because their products are more popular. So people just don't want to be troubled by having a different file format other than what they have, what their software or printer has. So that's another factor when you talk about the file format, popularity of file format. I think we can stop here, and let's go back at 11:10 for the next half of the class. All right. Okay, let's continue the class. So as I mentioned, there are some new file formats. And for example, these ones, the VRML, OBJ, and PLY. So these file formats support the colors assigned onto each of the triangles or vertices. And that will be a good asset for many 3D printers which have the printing ability of multi-colors. So for example, you can see here, this is printed using the Stratasys J750. And it takes the VRML file, and you can see how good the color look like. But it's not achievable using STL file. It just done, I mean, at the time when people define STL file, there's no consideration of the color, and they cannot they cannot foresee there will be 3D printers which are able to print multicolors. So because of that's the case, in the STL file, there's no such a color information associated. So another very important aspects for the computational parts of 3D printing are the transformations. So I mean, more specifically, translation, rotation, and scaling. So as I mentioned, during the slicing, you always want to move or rotate the part such that you could adjust the position and orientation of the part for the purpose of placing them on the bed of the machine, and also reduce the requirement of a support material. Also, for the design, 3D design you made, sometimes you just want to scale it up or scale it down to satisfy your need of the size of the part. Also, the CAD software versus the slicing software could have different axes. I don't know whether you have any idea about the some of the CAD software. They use the left hand system, using the left hand rows to define their coordinate system. On the other hand, many slicing software utilize the right hand row to define the coordinate system. So that will sometimes just make the 3D object flipped if you import the model from one system to another one. And that could cause problems for the slicing and the printing afterwards. So that's why we want to do some such kind of manipulation in our transformation in terms of translation, rotation, and scaling, right? For such transformation, what you could do is the matrix multiplications. So basically, you can convert each of these transformation into one transformation matrix and multiply this transformation matrix by the coordinate of each of the vertices. Then you will have the new coordinate of the vertices on the model such that the transformation would be completed. And that involves the matrix multiplication computation, right? And I think from your knowledge of linear algebra, you should understand if we have two matrix A and a matrix B, the condition for you to multiply them two together is the row. I mean the row. The column of the matrix A should be the same as the row number of the matrix B. So that's the condition. You could multiply the two matrices together. And here shows a detailed steps when you do a multiplication of these two matrices. So if you understand this, then for a vertices x, y, z, xm, ym, zm, and if you want to translate the vertices by a distance of a, b, and c, what you essentially do is use this translation matrix and put a, b, and c here, and then multiply this matrix by this vector, this 4 component vector, and the first 3 components are the 3D coordinates of this vertex. And it turns out once you complete this multiplication, you will have a new vertex position which reflects this translation. And there's one thing you want to keep in mind, that is the transformation matrix will be always on the on the left-hand side. See, this is the transformation, and this is the coordinates vector of that vertices. So this is for the translation. And if you look at another transformation, which is rotation, same thing. Put the rotation matrix to the left-hand side, and then multiply it by this coordinate vertices. Coordinates vector plus this 1 component, and it turns out after completion of the matrix multiplication, you will have the new position with respect to this rotation. And here it shows a rotation of the vertices by an angle of theta about the x-axis. So the rotational axis is the x-axis, and the rotation angle is theta. And it turns out you will have such a rotational matrix. And basically what you want to do is put them together. All right. Any questions so far?
I have a question.
Yeah.
What is the purpose of the 4th row in the matrix?
What was that?
The 4th row in the matrix?
You mean this one, right?
Yeah. What is the purpose of that?
Yeah, that's a good question. So that is if you basically if you talk about only look at the rotation and the translation, it seems there's no use for this. But if you talk about the scaling, there will be something here, put here. And then that will make this different. And the purpose to put here is we want to have a unified way to compute the transformation. No matter it's a translation, rotation, or scaling, you always do the same matrix multiplication. And but this only works when there is a scaling. Yep.
Thank you.
So I will show you later. There is a scaling case, but here that's the rotation about the x-axis. All right. Does it make sense to you?
Yeah.
Okay, good. All right. Similarly, you could also rotate the model about the y-axis, and the format, the form of this matrix is something like this. Same thing, right? And also for the z-axis, it's something like this. But for the scaling matrix, that will be something like this. I made a mistake, sorry. So basically the scaling here is you have these ones on the diagonals. And that means the scale factor along on the x-axis, y-axis, and z-axis. And this will be, sometimes you have the same scaling factor, and sometimes you could scale the model differently along different scaling I would say factors. So for all these, as you can see here, it has nothing to do with this force component. Actually, I made a mistake. Sorry about that. So even for the scaling, so for the scaling, it's still the diagonal of the first 3x3 matrix. So it has nothing to do with the force elements. But there are other transformations which are not listed here, such as sharing or twisting. Then there will be something different here. And there will be something which is associated with the force element of the coordinate. And that is not required for you guys. So, but for the translation, rotation, and scaling, you only care about the 3x3 in this case. And that's another another thing. I think I made a mistake. Sorry about that. That's one thing I didn't realize. So for this one, for the translation, see, if you have this this matrix, this is the what you want to do is, let me see. Yeah, so basically this row will multiply this column, correct? So what it does is 1 multiplied by xm, and these are zeros. So the components of y and the z are zeros, but then you will have a multiplied by 1 and plus xm. So what you have is xm plus a, and the same thing for the y is it becomes ym plus b, and this becomes zm plus c. Because there are 4 columns of this matrix, you have to have 4 rows to complete, to enable this matrix multiplication. That's why there's a force element. Sorry about that. I made a mistake. So that is why we need these force elements of the vector, because of this translation. And also there are other transformations than these 3 requires the force element. But even for the translation, it requires it. So any questions? Does it make sense? Does it explain your, I mean, the questions you guys have?
Why does that matrix have the 4th row though? Like I understand why the vector does, but the matrix seems like it's unnecessary.
Oh, because you have the, you mean this one, right? So
Yeah.
so which part are you talking about?
Yeah, that part.
This is a 4x4 matrix, right? and this is the 4x1 matrix. And turns out you have, so the number of column will be 4. This one and this one should be the same. So what you are suggesting is taking this out, right?
I'm not necessarily suggesting it, but just kind of asking why.
Yeah. So you're saying this one could be taken, right?
Yeah.
And that becomes 3x4, and still that will give you the answer, right? So actually you are right. In the case of translation, there's no effect if you even take this row out. It becomes 3x4, and turns out it will become a 3 vector, and there's no such a component for the resultant vector. So I think it's either way is fine, but that there's no cost to leave it here, because I mean, no matter how, this will still give you 1. That it does not actually, it doesn't require any computation. So in that sense, you could just keep it 4x4 and make it a square matrix. All right. Any other questions so far? So as you can see, we have all those transformation to be represented by a matrix, right? So that means for all 3 different kinds of transformation, we could use a unified way to do the computation. That is a matrix multiplication of the transformation matrix and this the vertex, I mean the coordinates of the vertices. So let's look at an example. So you have a point 0, 0, 1 that is somewhere here, right? It's on the z-axis, and offset from the origin along the z-axis by 1, right? And then you want to translate 5 units in the y direction, and then rotate by an angle of 90 degrees about the z axis. So what will be the new coordinate? So here are 2 transformation. One is the translation along the y-axis by 5 units. Another one is a rotation matrix along about the x-axis, and the rotation angle is 90. So what you want to do is just follow the order and do the transformation 1 by 1, and essentially that will be 2 matrix multiplication. So first is the translation. So basically you just, here are the x component, y component, and z component of the translation. But in this case, there's only one component that is on the y direction, in y direction. So put 5 here, and all the rest will be remaining the same. And the point is 0, 0, 1, and it turns out you have the translated point. Then the second step is the rotation. So this is the rotation along the y direction, and then go to how the y, the rotation about y look like, right? Find where are the cosine and the sines, and substitute the angles 90 here. And turns out you will have this matrix and multiply it by this translated vertices. Remember, take the result from the first step here to here, and then multiply and put it here and complete the multiplication. And finally, this will be the final position of that vertices. So this is how it works. so as you can see here, we could do a multiplication of these transformation one by one, and alternatively, we could compose the transformation first, and then just multiply the overall transformation or the concatenation transformation to the position of the vertices to have the final position of the vertices. And that is what actually those CAD software does for this transformation. So in that case, what we do is we first do the computation by put the two matrices together. And from the right to left, that follows the order of the transformation. You first do a translation, right? Then put it to the rightmost. And then you do a rotation, and then put it to the left-hand side of this translation. And then multiply the two matrices together, and turns out it gives you this final matrix. And also to partially answer the questions a student have, that is why to make it a 4x4. I think that kind of give you another reason. That is, you want to do such a matrix composition, and you want to make these to be compatible for this multiplication. And the best way to do it is to make it square matrix, always 4x4. Then you can multiply each of the transformation one by one till the end, till you have no other transformation. If you make it 3x4, this is 4x4. I mean, it's still fine. But what if you have another matrix, another transformation here, right? And that's another 4x4. I mean, here and here are not compatible. Then you cannot do the transformation multiplication again. So that causes trouble. So how about we keep it 4x4 all the time? Then we can always do the multiplication and do the transformation. I think that's a even more complete answer to the questions why we have the matrix like this. Any question? Okay. When you have this overall transformation matrix, you want to apply it onto the original position, and that's simply matrix multiplication, right? That's how you could complete this transformation. So there could be questions to ask you to generate this concatenation matrix instead of apply them step by one by one. And or there could be some other question which just ask you to apply them one by one and see whether the result of the method A and method B are same. And that could be some questions in your homework and as well as exams. But the purpose is to make sure you understand such a processes for matrix for the model transformation. All right. So the typical so basically if we look at the 3D printings, the typical task will be first to prepare the 3D model, right? It could be the surface reconstruction from some scanned data, right? Because we have a 3D scanner, we could turn the physical object to a digital file by scanning this digital object, the physical object, and convert the scanned point cloud to a surfaces. Of course, there could be some damages on the surfaces. That's why there requires a repairing. Also, colors, right? Because we have the capacity for printing different colors, then applying colors to the model becomes possible. There could be some optional, I mean, even the color is optional, right? You could just leave it a single color, a unicolor. Also, there could be some other options like you insert a lattice structures to reduce the weight, to hollow the model. I mean, that could be another editing to the 3D model to be printed. And there are some softwares available. You could take a look at it. And they are freewares. So you can just go to their website and download it and install it on your computers. Such as the Mesh Lab, it has quite a lot of functions to edit the 3D files. And another one is Autodesk Mesh Mixer. It also provides quite a lot of tools to repair, to edit the 3D files. And one thing particular for Mesh Mixer is its ability to compose two models. That is, you can take like for example, you can take a head from an animal statue and insert it to some other shape, such that you will have a composed new shape. So and it's very easy. Just to use some drag and drop functions, you could complete such kind of mesh editing, which is really convenient. And you could find it through this website. But let's look at the most fundamental processes for a 3D printing. That is slicing. So as I mentioned, for the slicing, it's like you are using a series of planes to intersect a given 3D model. And then you have the contour generated. And based on the contour, there will be infill generated inside of the contour. And these infill will also be converted to G-code. So the G-code will control the motion of the printer, the printing head and the printing platform. And that will be essentially what the 3D printer understands to print the model, right? That's the major processes for a complete cycle of file processing for a 3D printing task. Let's take more detailed look at this layer slicing, right? So as you can see here, we have the original shape, which is a semi-sphere, and you could slice it with a really thickness. For example, you only have 5 layers to represent this shape, or you could instead have 10 layers to represent this shape. You will see immediately this 10-layer slicing has a much better shape approximation compared to this 5 layers slicing. And essentially, the layer thickness will control the number of the layers. If you have a larger layer thickness, it turns out you will have more, you will have smaller amount of layers, and turns out the shape approximation will be worse, right? Or you could choose a smaller layer thickness and have more layers. And as a result, you will have a better, in general, better shape approximation. And this kind of a shape approximation is usually called step effect, because these layers just look like steps from this cross-section view, right? And if I ask you, how does the layer thickness affect shape roughness, you should be able to answer it, right? The larger thickness will make the surface rougher and more rough, and a smaller thickness will make a finer surface, right? So what the slicing does is basically use those slicing planes to intersect the 3D model, right? And for these slicing plane, basically it's not just one plane, it's a series, a family of plane. And these planes are parallel to the XY plane and has different Z's, right? And this Z, the offset along the Z axis will be the layer thickness. For example, the first plane is Z equal to 0. That means the bottom of the model usually, right? And then if you go up a little bit and make the Z equals to T, which is the layer thickness, actually you have the second cutting, slicing plane, and then you have the second layer. And then you go to Z equals to 2T, and that will be the third layer, and so on and so forth. So here gives you the idea. If you make a 0.1 layer thickness, then the first layer will be here, and here, here, and go on, so on and so forth. So there is some terms showing here, which is the trigger point. So basically the trigger point is a point where a slicing plane cuts through a facet's edge. So what basically to compute the intersection of the 3D surfaces and the cutting plane, what we do is actually we are computing the intersection of the slicing plane with the triangles in the STL file, because the 3D model are represented by the triangles. So what actually it does here is just the intersections of these slicing plane and the triangles, each of the individual triangles. Of course, there could be some triangles which are not intersect with the slicing plane, but there are cases the triangles intersect with the slicing plane, and the intersect points are these trigger points. All right. So any question about this? All right. So as I mentioned, there will be the contours and or loops, right? Just imagine you have this semi-sphere, and once you cut it, there will be a cross section, right? Something like this, right? Just like the one shown here. But for the model, there could be some holes, right? Let's say you have a model like this. So basically that's a cylinder, but you have a hole here. I mean, that's quite normal when you cut a mechanical part. In that case, if you slice the model, and there will be two loops. One is the exterior loop, and another one is an interior loop. So in the slicing computation, it usually defined the loop for the exterior surface have a counterclockwise direction. I mean, counterclockwise order. And the loop on the interior surface have a clockwise direction. So if we look at this slicing, that means, well, the loop, if you check each of the trigger point on the loop, it follows, it will be ordered in the counterclockwise. And similarly, if you check the trigger point on this interior loop, it is in the clockwise order. So why we want to do this? That is because when you print the part, the printing nozzle actually needs to, for example, you want to print something near this this loop near here. Actually, the nozzle will be located here because there will be an offset from the center of the nozzle to actually the loop, right? And then you want to compute a offset from this contour to the interior of this region. So in this case, you want to offset to the to the left hand side. If you just imagine you are standing on this loop, and your head is pointing towards the counterclockwise direction, then where is your left? Tell me, where is your left? Come on, think about it. Just imagine you are standing here, and your head is pointing along this counterclockwise direction. Then, which side is your left hand side? I mean, which side is your left hand side in this case? Yeah.
The inside.
Yeah, exactly. Your left hand side will be interior of this loop. So that is where you want to offset the position of that is where you want to offset from this exterior loop to find out where your nozzle should be, because your nozzle should be here, such that you can print the model like this. If your nozzle center of nozzle is located here, then you will put some extra material outside of the loop, and which is not desired, right? So that's why you want to always offset your nozzle to the interior of this loop. And if we define the loop orientation is counterclockwise, that is offset to the left-hand side of this loop. But that's for this exterior loop, right? But if you look at this interior loop, and again, the loop is in the counterclockwise direction, and still you cannot place the center of nozzle here. Otherwise, it will print something here. Still, you want to offset the nozzle to somewhere here, the center of nozzle to here. And again, if you stand on the loop, and let me draw it better. If you stand on the loop and point your head towards the clockwise, in this case, clockwise direction, then where is your left? Where is your left-hand side?
On the outside.
This side or this side? The white region or the black region?
The black.
Exactly, the black region. So as you can see here, because you have different orders for the loop, that is for the exterior loop, it's counterclockwise. For the interior loop, it's clockwise. Therefore, when you do the offsetting, the only thing you want to do is just to offset to the left-hand side of the loop. And that's it. That will make sure the material will be put to the model, to the correct region of the model. So that's why we define this orders for the exterior and the interior loop, and that make the control of the manufacturing process easier. Then another question, it's a little tricky here. Does it make sense to you, or any questions? I don't want to have a questions and go further. I just want you to fully understand it. Any question? Okay, good. Some extension, it's not required, but you want to have some basic concept. That is, well, when you do the slicing, and you could have multiple loops, right? But the thing is, how could you know which one's interior loop, which one's exterior loop? And that's a very interesting geometry questions. Actually, what people did is, let me remove this. What they do is they check the loops one by one and find all the combinations and see if a loops, all the points are inside another loops or not. If there is any loop, any points of one loop is inside another loop, well, that means that's a interior loop. Otherwise, it's an exterior loop. So in this case, basically, you will compute all the points of this loop, see whether it's inside of this one. Similarly, you will compute all the point of this loop and see whether it is inside this one. Obviously, it's the first case, right? So that indicates this is the inner loop and this is outer loop. I don't want to go to the details, but just let you know, even such a simple, for our human, it's simple, right? You by looking at this, you will immediately tell which is the outer loop, but inner loop and inner loop. But for an algorithm, it makes no difference if there's no other checking or adjustment or judgment made, and there's no difference for them, inner loop and outer loop. Right? That's very interesting. Okay, let's move on. So in order to efficiently and effectively compute the slicings, there should be some data structure created. Basically, you probably want to have a data structure including the vertex list, edge list, and the facet list. So what they stored are the information of vertices, edges, and facets, such as the coordinates of the vertices and the facet and vertex list for the edges, the vertex list for the facet, and so on and so forth. Also, some of the adjacent informations like these. So for the edge, you want to know what are the two vertices. And for the facet, you want to know what are the three vertices to form this facet. And sometimes for the edge, you want to know what is the two facets share this edge. It will speed up the computation of the slicing. And let's look at this illustration. So basically, if you have something like this, and this plane shows a slicing plane, and what you will compute is the intersection of triangles with this slicing plane. And if there is an intersection, that means there is a line segment in between of this cutting plane and the triangle. For example, here, see, these are the line segments you want to store and use to form this loop. All right, basically you want to connect the line segment and store them one by one. Of course, you want to make sure the end point will be the starting point. I mean, the end point of the previous line segment will be the start point of the next line segment, and that's the way you want to order these line segments and form a closed loop. So for the intersection computation, what we want to do is to utilize this 3D plane equation. This is a form of 3D plane equation, and where x and basically no, I made a mistake. This is not a plane equation. Instead, it is the edge equation, the triangle edge equation. And if you look at this this illustration, if we have a triangular edge with two endpoints, P1 and P2, and P1 has coordinate, 3D coordinate x1, y1, z1, and P2 has coordinates x2, y2, z2, then this is the 3D line segment for equation. So this represents this 3D line segment. So what you want to do is to use this 3D line equation together with the equation of cutting plane, or I mean the slicing plane, to find the intersection, to see whether there will be an intersection or not. So there's one known, that is the z, right? Because we have generate a series of slicing plane, right? Basically, each of the plane will be the offsetting of the previous plane by the layer thickness, right? And these are all preset. Before you do the intersection computation, you should be able to have these series of plane already in hand, right? Then what you want to do is to put the two equation, I mean the plane equation, the slicing plane equation, and the 3D line segment equation together. And there are two equations and two unknowns. Then just to solve them, you will have the intersection points. Here, just to list the x and y coordinates of the intersection point or the trigger point. Why? Because z is known. See, for the cutting, for each of the slicing plane, when you find the intersection, the z coordinate is always the one identical to the z components of the slicing plane, right? That is known. So the only thing you want to compute here is just the x and y, and that's it. So remember these two equations, and that will be always used to compute the intersection or the trigger points. Any question for this? Okay, great. So for example, we have a triangular edge with 2 points. One point has a coordinate 1, 3, 2, and another point has a coordinate 4, 7, 6. And then you have the slicing plane at a height of z equals to 3. Then what is the intersection? What is the trigger point? That's simple, right? So what you want to do is just substitute these numbers to the two equations here, and it turns out you will have the trigger point computed. And remember, again, this z is known. You do not need to compute it. So also there is some other ways to speed up this computation. I think we do not have enough time to explain it. Okay, let's stop here, and we will continue discuss the slicings, and also as well as some of the support generations. And together with the two, I mean the slicing and the support generation, we will try to estimate the total printing time if you have a model given and some parameter known. And that will be possible to be some test questions or questions in your homework. All right. So before I let you go, any questions so far? All right, good, good. And okay, I think that's pretty much all for today's lecture. And again, for the student who hasn't submitted the homework one, please submit it by today, such that I could give the grade, still give the grade. All right. Yep, that's pretty much the end of the lecture, and see you guys.
See ya. Have a great.
Thank you.
Yep.
Thank you, Professor.
Yep.
Have a good week.
Yep. Thank you. You too. No problem.